Hi, this is Diego, and I'm going to give you an overview of what you can find in our paper about our experience in advanced network operation in unconnected remote communities. Our deployment is provided by the Temporal project, whose goal is to provide sustainable mobile broadband to unconnected people in Latin America. Specifically, we're going to focus on one country where the project is deployed. The project is an infrastructure project, providing infrastructure to different mobile network operators who want to provide connectivity. It leverages a revenue sharing model where the revenue are shared between the mobile network operator and the infrastructure provider, and it leverages open access technologies. In the country we focus on, there are thousands of small communities, having 2 or 3G connectivity mostly. Some of them also have 4G connectivity involved. These are really remote areas. Most of them are on mountains, some on the coast, and actually some are even in the jungle. It is worth noticing that the average distance from the main road of these communities is 8 kilometers, but some of them are tens of kilometers away from the main road. These communities are equipped with different power supplies, including solar panels, power gear, and battery. Some of them have a combination of those. The project uses heterogeneous third-party backhaul according to what's available. It's either radio links, satellites, and fibers. And as these communities are spread across an entire country, operation teams are organized in 40 roads and controlled by a centralized entity and a ticketing system. Different KPIs and different network metrics are collected from different sites. As we have different vendors technology that are deployed, there are different ways the alarm collector collects this alarm. After that, all of these alarms are cleared and stored in an alarm backend with different status, either the alarm is active or has been cleared. There are actually 3 main failures that can happen in our operation. One of them, and the most present one, is the GSM cell being out of service. Also, another problem that often happens is that actually the cell doesn't have power supply. One that is also present but less dominant is the return loss at the antenna port. Based on these alarms and failures which are collected, there are different applications that the operation team can run. For instance, it can run a rural bot that tells the operation team what to do and which sites to go next. And there are, of course, a lot of dashboard, monitoring dashboard and diagnostic dashboard. And in our advanced network operation, the idea is to build on the top of these alarms, statistics, and measurements to help the operation team improve their daily work. And we're going to talk a bit more about this later. I'm presenting here some analysis of the data collected over 5 months in our deployments in these small cells. On the left-hand side, you see the duration of the alarms on the failure, while on the right-hand side, you see the inter-failure time. Takeaway message here is that most failures are temporal. They last less than 1 hour, many of them also less than half an hour. And these temporal failures are due to backhaul saturation or battery outage, which are also temporal, some of them at least. So as all these sites are really remote and hard to reach, it's very important not to schedule an intervention if the failure is temporary, is gonna go away right after. So it's important to have control and predictive mechanism to avoid costly and unnecessary intervention. This is a typical example where advanced network analytics can help. It's also very important to understand the nature of the failure in order so the team will be equipped with the right elements to go to the site and fix the problem, as it's not possible to carry a solution for all the problems, especially in this remote area with long distance. So, as an example in the paper, we talk about the problem of detecting if a failure is temporal or not. And we show that machine learning techniques can actually reduce the costs of operation from 5 to 20%. Of course, the cost depends in the cost model, which in turn depends in the value of the cell, depends on the number of users, presence of other structure, and the cost of intervention. We try different techniques ranging from simple machine learning algorithm to advanced deep learning techniques, and actually good machine learning techniques like XGBoost can work well in this environment. Also, we found that machine learning can help the definition of heuristic that can help when operating the network. So what you will find in the paper, you can find a description of our deployments in thousands of small communities. You will find what are the challenges in managing such large network operation in these specific remote areas. You will find a 5-month characterization of the failures and alarm pattern in the system, and you will find details about how we build an advanced operation support system, including machine learning and analytics support.